So the program I prepared for today is about decision trees and random forest. And to discuss random forest, we need to discuss also ensembles. So we will go through this step, and then it will be as a hand-on exercise. And let me introduce random forest. It's like the Swiss knife technique of machine learning that is used for everything. And this was the technique that won the machine learning competition we host here on predicting the Mars Express thermal power consumption. We also applied for integral, for instance, to predict the radiation belt entry and exit, and also some other project. And it's quite famous because there is a machine learning competition website called Kaggle, and this technique of random forest is often among the one used for the winning solutions or winning teams. No? So a random forest really is an ensemble of decision trees. So I figured out that if I tell you what is a decision tree and an ensemble, then you will know what is a random forest. So there we go. And the best way to explain what is a decision tree for me is with an example. So this example we discussed last time, but I repeat again for those who couldn't attend last time. We have these three flowers, or three varieties of iris, and we have setosa, versicolor, and virginica. And we know which is the length of the sepal and the petal, and also the width. And with this information, we need to understand which flower it is. So I will do this with a decision tree, which is a very simple decision tree, and this will allow me to carry on with the discussion. So that's a decision tree, and let me put a laser pointer, a virtual laser pointer. So what you see here is some decision that is made based on the features. The feature we have are 4 features. So we have petal length, petal width, sepal length, and sepal width. In this case, the sepal information was not needed because everything could be derived from the petal. And the way to read it is the following: is in the first node, we have 150 samples. And at this moment, we didn't make still any choice because we didn't have the time to ask any questions. So we have 50 for setosa, 50 for versicolor, and 50 for virginica. So we don't know yet. And in total, we have 150 samples. And the question we ask is the petal length less than 2.45 centimeters? If this is true, then we know it's setosa, quite easy. And we have 50 out of 50, so little uncertainty there. If this is false, meaning that the petal length is more than 245, then we check the petal width. And if it is less than 175 centimeters, we end up in this leaf node, meaning that we will say it's versicolor, otherwise we say virginica. But this time it's not so clear because we have 49 out of 54. So we have more probability to be there, but it's not exact. No? Same here, we have a high chance. And that's why, in addition to getting these classes, we can also get probabilities. So here is probability 1, probability 0.91, 0.98. So we can get the computation of probabilities also for us. There is something I didn't explain that I want to explain now, is this Gini number. It's a measurement of purity, because the way the tree is built is that you want to have every branch to increase the purity of the branches that you divide. The formula for the Gini is this one, which maybe is a bit weird, but you will see with an example how easy it is. For instance, for this green node is 1 minus the probability of each class. So 0 divided by 54 to the square, 49 divided by 44 to the square, you get it? No? and you plug this, and you get the Gini, and correspond to this purity measurement. Okay, so I can tell you how the tree is built. The tree is built following a greedy optimization. So greedy means that at every time it will pick up the node that maximizes this Gini split, and we will never be sure if this tree is the optimal tree. So there will be a good tree, or maybe a very good tree, but we never know if it is the best possibility of tree. The thing is that if you want to be very sure that it's the very best tree, they will be very computationally expensive to compute that. So the way it works is that for every node, for every decision, we want to optimize this cost function. So F is for the feature. For instance, feature in this case was the petal length, and the threshold. The threshold we set here less or equal to 45. And what we want to optimize is the Gini, so the purity on the left side, the purity on the right side, and this will be weighted by how many samples go to each side. So quite simple is we want to optimize or make as pure as possible each side of the branch, weighted by how many sample fits there. Okay. We can also get from the tree feature importance. So you can train a tree with your data, and it automatically tells you how important each feature it is to find the class. This is for classification, but what if we have regression? We can also use trees to do regression for us, and it's actually quite similar. When we say Gini, what we want to do instead is to minimize the mean square error. Let me just make a reminder for the mean square error. What it is basically you compute the error from your estimation, if this would be a line, for instance, and you square the error and do the average, basically. So here what we're doing is we're trying to reduce the mean square error and find which feature, which in this case quite easy because we only have one feature, which is the x, and with threshold, by doing the splitting, we minimize the mean square error. But it's just the same idea. I want to talk also about regularization, because if you have decision trees and you let them to do as they like, what they will do is that they will create a node for every point, because like this they reduce the error. But you see, this is quite a bad idea if you're thinking of generalization. Sorry, say? This is a function I created. So is this one. So I invented it. This function is nothing. I invented this function just to make the point. This doesn't generalize well because it fits the noise data. So one way, for instance, to regularize is to put some constraint on how the tree is built. In this case, what I said is that every node at the end, so the leaf node, should have at minimum 5% of the samples. So by doing this constraint, you don't allow it to be split forever. So the kind of constraint that you can put is what is the maximum depth, so how many levels of depth you want. You can also control how many nodes you have as maximum. Minimum side, you can control the minimum number of samples, or the minimum number of samples that the node must have before you can split it. So by requiring, by making the maximum number smaller or the minimum numbers bigger, you are regularizing how the tree is built. Decision trees don't make any sort of assumption. So it's not like a line or a polynomial or so. If you have a line, you know that your solution will look very much like a line. Or if you have a polynomial, will look a polynomial and so on. So they don't make any assumptions. And for me, this is good because they can learn anything. So they can learn like a polynomial, they can send a sinusoid. So this is where they shine because they can learn whatever. On the negative side is that since they don't make any assumption, if you don't have data for them to learn from, it doesn't learn anything. You see, it's a total failure here. This polynomial or this sinusoid, after the range of data you provided, is not really able to realize that this is a sinusoid function. Okay, so this is as limitation. This for decision trees. Now I'm going to explain a bit how the ensembles work. And the ensemble is nothing more than having a group of machine learning models. And what you have is that each model in the group produces a different prediction, and you combine all of them. Okay? And depending on how you combine them, you have different kind of ensembling. We're going to cover today voting and bugging, but also for you to know, there is also boosting and stacking. If you're curious, then we can discuss them after. So the voting, I think, is quite easy to guess. So you have some machine learning models that are already trained. What you do is, when you have new data coming in, you get the predictions of each model individually, and then you do majority voting. So why this is a good idea, why this makes sense? And it makes sense because each model has different assumptions, and each model has different error. So somehow the error compensates for each other, and you get something or you get a prediction which is often better than if you will not combine. This is for voting. For bugging is what we need for the decision tree. What is the same concept, so it's like voting, but instead of using different machine learning models, is doing voting with the same model. So we're going to vote with several trees. The thing is that if we vote with several trees, this nice effect that the error compensate to each other, we don't have that, because all the trees will be the same. I mean, they are built randomly with a node to choose and so, but at the end, the best node is the one that minimizes the error, so you will be getting very, very similar trees. So you will not have this effect of compensating the errors. So we apply a trick to make the decision trees look different. And the trick is quite simple. You have your training data, you do random sampling on your data so that you have the same model training in different pieces of the data. So none of this model sees the whole data. And then when you have this model trained, you have new data, you get the predictions, and you do the majority voting as you were doing before. When it happens that this model are decision trees, this is what is called random forest. Okay. I want to mention something because I'm saying that we are doing the voting. In reality, it's a soft voting, so it's a bit more complex. I come to this in a minute. Random forests are good for generalization. So this is on the left, you see a decision tree. But if we want to feed the same data with a random forest, this is what you will get. So usually, what you get is very similar training error, but the testing error, so the error you want to have to minimize so that you are able to predict in the future for data you don't know yet, is much smaller. So that's the reason why they are so good to do predictions in the future. So how the results are combined? For classification, is with the majority voting, but with a trick. It's called soft voting. So we combine the probabilities in a way that those having a more confidence get a higher weight. So it's not really majority voting, it's weighted by the confidence. For regression, the typical approach is to do the mean value. So you take the predictions from all the trees, you take the average, and this is your prediction. We don't need to do it like this. We can invent our own way of doing it. And here's an example. What you see in the black line is the average, but these red lines is the prediction of all the 100 trees in this random forest. So you can combine all these predictions in the way you like. And something that I did is to get the minimum and the maximum. And you have like an envelope, which is dynamic. And for instance, here you see that the maximum is less certain than the minimum. I mean, the data is noisy and so, but still makes sort of sense, no? So, what should you take? Decision trees or random forest? This is my take on it. Decision trees are good if you're interested in inspecting the tree. So it's a white box model. And if you want to understand how the prediction is done, they're very good because they discard what is not needed and tells you which question to ask first and how you should go. For random forest is that if you don't mind using a black box model, it's not truly black box because you can inspect every tree, but I don't know how much insight you get by examining trees that has been generated with random subset of data. So I will use them if for you it's more important predicting than understanding. So if you want to generalize in the future. What I will do, or what I like doing is doing the both of them. So I use the tree for understanding and the random forest for predicting. So you can do these two because the training error will be about the same. It's only the generalization error that you improve with the random forest. So my message for today, random forests give you forecasting powers, but only if your data is similar to the training data. This is not as bad as I pictured in this figure, because usually what happens is that you have many features. So you don't only have X like this one, you have maybe 100 of features, and maybe one of them is outside the limit, or the range that you use, but all the other are inside, usually. So it's not as bad, but also I want to put this picture to say that it's not more magical than what it feels. No? So for hands-on today, what we're going to do is to solve a direct marketing problem. And there is a Portuguese bank that collected some data and made this data available for machine learning. And the task is to predict if a term deposit, so term in the sense that 1 year deposit or 5 year deposit or so, will be subscribed or no. And this is good because they want to save costs in the sense that people calling every client, you are interested in this product, yes, no, so you save time. You get more deposit if you can figure out who will be interested, and it's much less annoying for the people who don't want to participate. The thing is that I need to introduce some concept because so far we've been talking mostly about regression, and we introduced last time the mean square error to understand how our error is. Since this is a classification task, I need to introduce another kind of how we're going to measure how good our solution would be. And I want to put you an example. This is called confusion matrix. It can be a bit confusing, no pun intended. And this is how to read it. So you have your data, which is as it is, the data which is real. And 0 will mean this person didn't buy the deposit or didn't subscribe, and 1, yes, he or she subscribed the deposit. And this will be our prediction. We predict she didn't subscribe, or she will not, or she will. And then you can have this combination. So the best will be to have something here, something there, and these to be zeros. But it's often not the case. And there is a terminology for this. It's called this true positive, true negative, and it's a bit weird. It took me also a while to figure out the best way to learn. And for me, the easiest is if you go by prediction. If you predict 1, it's always called positive, because you predict it's positive. If you predict 0, it's negative, because you predict negative. And then true or false depends if you were right or not. Okay? And based on this information, you can compute this measurement like accuracy, precision, and recall. And for our data, for this example, this will be the values. What I want to say is that rather than going the formula, is that accuracy is quite misleading. So even if we have this model that we have 75% accuracy, this is quite bad, because this accuracy is because when it's the majority of the time is the person doesn't take the deposit. This we know, it's intuition. If somebody calls you from the bank, I usually say no, or most people say no. So if we just predict always no, we will get like 70% accuracy. So this doesn't take into account this fact. So it's much better to use this precision and recall. So precision tells us the quality of our prediction, and recall tells the quantity. So quality is in the sense that we take into account these two cases. So, for instance, this means that we will call 15 people, and out of these 15 call, 5 will say, yes, I will take it. Okay? So there we measure the quality, how effective we are. And recall is the quantity. The quantity means that in reality, these people, so the 15 plus 5, will be interested in getting it, but we all identify 5. So precision is more like quality, and recall is quantity. And it's always convenient to have a number to combine all of them. So this is called the F, or the F1 score, and this basically combining this measurement. Okay, so before starting the hands-on, just to tell you, the material will be on the ESA Connect data analytics community. And the next session, we will talk about neural networks, deep learning, and there will be also some hand sessions. So the next session will be Thursday, March 22nd, on the press room. So thank you. And before we start the hands-on, maybe if you have some questions on this topic.